Great. So we discussed VM crashes, and Apoorv suggested we can recover. Uh, I'll quickly show you a demo of a very nice utility that I've been using since the past few years. It's called PS Util. So it can give us various different Second last. So it can give us various different properties which you would have otherwise accessed using the PS command or certain other command line arguments. So for example, I get the percentage of CPU utilization is 14.9, fairly low. So you can also set per CPU. So now you get, so my system has 4 cores, and you can also verify this. CPU count 4 cores. So we have seen something regarding CPU. We can see, so it gives us the battery percentage also. So I'm sure this would be now giving you some ideas on cool stuff you can build. So if you now recall that in the first lab we saw the task manager in Ubuntu. What is that called? Do we remember? System monitor. So now you can build a system monitor on your own because it's just an API now to invoke. And let me just give you one quick demo of a program that I wrote. So this is showing the CPU utilization in real time. Now this is a very quick hacky program that I've written. So one of the problems is that it just keeps on accumulating data points. So you might want to look at only the last 100 odd points. So that's a very trivial fix to this program. And if you're really adventurous, you could also do it on a per CPU basis. So for each of the different cores, you can now show the load. And so I remember using PS Util in 2013. So I was using Raspberry Pi to collect some data from a smart meter. So think of smart meter as a meter or electricity meter, and it will give you real-time electricity consumption. So Raspberry Pi was collecting the data, and I was observing that every 1.5 days or so, the Raspberry Pi would just freeze. It would stop collecting data. So I ended up using PS Util to monitor all the parameters, the free memory, the free disk, the CPU utilization. And I thought that eventually through all these debugging process, through logging process, I'll be able to figure something out. Eventually, I used a hack. I would restart the system, reboot the system programmatically every day. So rebooting usually works in such situations.
Why is there a huge variation in the CPU?
I think so. So firstly, this method is not perfect. Not perfect as in, I think it itself might be adding to the load. Plus, it's looking at the instantaneous load. So at one particular millisecond, you might have the one process kicks in, the load might be high. But if you look at on an average of let's say 2 seconds or 3 seconds, so you'll see that the load is generally low. So we'll quickly revise direct execution, which we started in the last class. So we create an entry for the process. We allocate memory for the process. We load the program into the memory. We set up the stack, execute call main, run main. The main, so we return from main. We free the memory given to the process. We remove the process from the process list. Okay, so anyone who remembers the challenges with direct execution? What's the problem in the previous direct execution flow? Yeah. So we cannot switch to another program because Right. So that's one issue. Any other issue? So again, if it goes into infinite loop, the OS never gains control. Right. So the other is illegal access or no security of protection mechanisms. So how would the OS stop the current process, run another process? How does the OS ensure that the program doesn't make any illegal access? I think output. We also said that one way to handle this could be to stop all network and I/O access, but that doesn't happen. So there's clearly a way in which we can mitigate this problem. And we saw that we can mitigate this by having two different modes, a user mode and a kernel mode. So basically the execution of the process, the CPU can be in one of these two modes now at any given point of time. And we can probably set up, so if we are thinking out, we can probably think, the CPU will probably have a bit corresponding to which mode it's executing it. In the user mode, the restricted mode, we cannot issue input-output. If we try to do that, it will result into an exception. The program will probably crash or close. But in the kernel mode, we can issue input-output, and this is the mode in which the operating system runs. How do we go from a user mode to a kernel mode? We go via syscall, which is trap instruction. We discussed about polling and interrupts yesterday very quickly. So again, a very quick pop quiz. Why would you prefer interrupts over polling? And this polling is not the same as your electoral polling. So polling means your right. So polling is continuously looking for something, whereas what you want is to look only for an event. Whenever an event occurs, an interrupt is raised. So we stopped at this point yesterday. We want to look at the difference between a trap and a function call. So I assume that all of us know what happens when a function is being called.
So how is interrupt exactly different than polling? Like it must look somewhere in the hardware if this voltage is high or not.
How is it exactly different from polling? So in polling, it's think of it as we've written some code. You are expecting it to occur in particular line of code. So it's synchronous kind of an operation, a synchronous kind of a lookup. Whereas if something happens, it goes to that pin. So there is an interrupt pin. Whenever there is, let's say, whenever there is data on the input-output bus, so then it only raises a bit, and that goes to that particular interrupt request handler. So I was assuming that this was probably taught in the architecture course or not. So handling interrupts was not. Maybe so. So there are different architecture courses. One is organization, there is architecture, and then advanced architecture. So I think maybe we started with an advanced architecture. So we have the program running, the program counter points to main. We have a function f of x, which says, let's say defined at this point of location. So this is again showing the address space of the process. I'm only showing the code and the stack. What is missing in the space? Heap. So let's say the program counter now goes to f of x, and this SP stands for the stack pointer. So what do you think will happen next? You'll store the state of the.
You have to return to the main program. So you
Okay.
store the return address.
Okay, and where do you then store this return address? We store it on the stack, and if you remember stack, so it's push and pop operation. So you build it one way and then you delete it the other way. So then the program counter, let's say the execution goes to this. Simultaneously, you will store the old program counter. So basically, what you want to do, the purpose of this is, if you have returned from the function, you want to go back to the same point where you were previously executing. So you pass in all the arguments, the old program counter, the stack pointer moves down or up based on the direction in the implementation. Let's say now the program reaches the last line of the function. So we'll again, in that case, we'll go to the next line following the function execution, and the stack is popped. The code will then again run as per the usual flow. System call is very similar. The main difference being that it's a system call. So system call is trying to access restricted portions of the hardware, or restricted resources. So let's say we have a system called like open. So we have the code which so effectively this is shown at this point of the screen. So we have a user mode and a kernel mode. So if the program counter is at main, the next line is go to an open, which is now a restricted operation. You cannot execute it in the user mode. So somehow you need to move to the kernel mode. So we discussed if you move to the kernel mode, the CPU has to basically have a byte, or basically has to bit, which now is going to be flicked. So it's somehow you need to ensure that the CPU is now in a different state. I've denoted that by putting a star next to the CPU. It goes into a different state. The stack pointer. So we still maintain the same notion of a stack, but instead of a regular program stack, we now have a kernel stack. So in the kernel stack, we push the old program counter, the arguments, and the program counter now goes to the trap handler. So instead of going to int of f of x, think of it as something similar, but something which is handled by the OS and not handled by the handled in the kernel mode and not handled in the user mode. So this is the complete picture of how this operation should happen. So we initialize the trap table at the boot time. So we'll have different types of traps. Different types of traps means different types of system calls. So corresponding to each system call, the hardware needs to know the address of each of them. So something needs to be initialized at the boot time. That is done in the kernel mode. So could something go wrong if you could change the trap table in the user mode? Or why wouldn't you change the trap table in the user mode?
I don't think the addressing points.
So you can create a complete havoc. So if the open system call was at address A, you change it to C, something really bad can happen. And the hardware has to remember the address of all of these system call handlers. So when we look at different modes of the OS, all of this has to be initialized. So if you're wondering what happens at boot time, this is one of the things which the OS has to do. Let's look at runtime. So now this is fairly similar to the flow which we have seen in the past in direct execution. So for each process, we create an entry. We allocate memory for the program. We load the program into the memory. We'll set up the stack. We'll fill the kernel stack with registers and PCs. So this is something new which wasn't happening previously. And we return from trap.
The kernel stack is a part of the memory of gates and process gates, like extended stack. Is it extended stack or is it different stack?
So the OS is going to maintain some of its own data structures. So it's not a part of the program as such. It's a part of the OS and it's a part of the hardware.
Also, it's different for each of the processes.
So so you'll have to maintain some data structures per process. For example, there is process list. So when we go to the part of virtualizing memory, so we'll understand that for each of the process there are certain more operations or certain more things we need to store. So it's stored differently per process. So we have we fill the kernel stack so that you can then start executing the program. Restore the registers from the kernel stack, move to the user mode. So at this point of time, so all the processes get created in the kernel mode. They don't get created in the user mode. We restore the register from the kernel stack, move to the user mode, jump to main, and now it's fairly similar to the flow which we've seen in the past. We run main, But let's say we execute a system call. Let's say it is open or fork or exec. That will create a trap into the OS. Am I clear to everyone at this point of time? Any doubts? Can you ask those doubts and help me to clarify? So this is slightly complicated compared to previous approaches we have seen thus far. What's not clear till now?
What is defining these two modes? What is the difference?
What is the difference between
These two modes, like how are you switching?
how are we?
Switching between two.
So the OS has to switch between this. You don't switch as a program. So assume that you've written a program. Now, if the OS didn't exist, how would you execute the program? So someone has to execute the program on your behalf. The OS has to do the bookkeeping, and so think of it. The OS is responsible to ensure that all the processes are running efficiently. So the OS takes the program residing on the disk, it loads it up into the memory. Now, there are two modes in which programs are being run. So this is being done by the OS. The OS resides in the kernel mode. So that's why loading of the program is done in the kernel mode.
Modes are basically set of rules by which the program will run.
So they are basically just two different modes in which a program can be executed. If there are any restricted operations, any bookkeeping operations, anything to do with the OS, that's the kernel mode. Anything to do with the user, very simple, trivial, non-restricted operations, that's handled in the user. Any other doubt in this point of time? The program stack is a part of the address space itself. Any other doubts at this point of time? Okay. So all of us now understand that whenever a system call is made, there needs to be, so whenever a function call is made, there is an address to which the program counter needs to go to execute that. Now, if we're doing the same for restricted operations, that address cannot be a part of the program address space. So that address and that code or that logic that follows has to reside somewhere else. So that has to be initialized by the OS. Now, when do you initialize that? The best time to initialize it is at the boot time, because none of the other processes have executed. So you create something known as a trap table. This is similar to something known as this is somewhat similar to creating an interrupt table. So basically, you need to tell the hardware, or you need to tell the entire structures of what should happen if I press a key, and all of that mapping is done at boot time. So you initialize the trap table, and you create for each of these handlers there is a specific address associated with it. So like open will have a different number, a different syscall number. Fork will have a different syscall numbers, and each of these are passed as arguments to locate the address of these of the code that needs to actually execute. And this is similar to what we've done in the past. So whenever a process has to be executed, we need to create an entry for that process. We need to allocate memory. Memory will contain again those properties such as that divisions such as code, heap, stack. You physically load then the program into the memory. You set up the stack with the arguments, and then you fill the kernel stack with the register and the program counter. Why would you do this? So let's think in different terms. So let's think that if there is a context switch happening, then will you set up the kernel stack with registers and program counters? You will do that, right? So think of it for every new program being invoked, is in some sense a context switch. And then you finally return from trap. You restore the registers from kernel stack. You change the execution mode to user mode. You jump to main, you run main. Again, if the system call is made, syscall handler has to be executed, but that will get executed only if you can create a trap into the OS. Whenever you create a trap, so as we saw, so whenever a function call was executed, we were saving the state of the program, the current program counter and the other arguments to the user stack, to the user address space stack. But since this is syscall, we save these register to the kernel stack, move to the kernel mode, and then jump to the trap handler. So jump to that piece of code which will now handle the input-output figure. The OS will finally handle the trap with syscall, return from trap. So this is now similar to return from trap. Once you return from trap, so you do the same thing. You restore the registers, move to the user mode, jump to the program counter after trap. So if you just look at this by itself, it might look complicated, but always look at it in conjunction with how a function call happens. And replace all the stack calls by kernel stack calls. The only major thing which is different is the usage of, is the execution mode, user mode versus the kernel mode. You return from main, which is you trap via exit, and then you free the memory of processor. Sorry?
Is the address of kernel stack fixed? Like, suppose a program stores something in kernel stack. Then
Right.
who remembers that where is kernel stack? From where to read the playback address?
Where is the kernel stack? What is the address of the kernel stack? So if you see running a general user stack, then that address is within the address space. I think the OS has to maintain that on a per block basis. So I think it will, whenever you're creating a process, it will remember, so it will maintain some kind of a data structure where you will store the starting address of the kernel stack. I think that's what is happening, but I'm not very sure. I'll confirm this in the next class. So I'll be honest that this is somewhat complicated, and so it takes me a lot of time also to understand this. So don't worry. And my understanding is also not perfect. So how do you switch between processes? Any ideas how do you switch between processes now? So what you need to do is a context switch. So I'm asking you how a context switch would look in terms of the execution flow we saw in the previous slide. Yeah.
So whenever we have control, OS has a control, it scheduler would decide which process to choose, and the hardware would do accordingly. Like it will restore the stack and arguments of that process.
Right. So let's say we have two processes A and B. If you want to context switch from A to B, you'll have to store all of the contents of the stack of A into, all of the program counters and certain other registers into the stack. And you need to restore the stack contents of process B. Yeah.
We are storing the registers and kernel counter in kernel stack, right?
Right.
Like just now you were telling that kernel stack is different for each process.
Sorry, didn't get it right.
Kernel stack is same for all the process, or it is different for different process?
So while executing, so let's think of it aloud. So again, if I'm wrong, please correct me. So let's all of us think together. So we have, so for each process, there is a user stack which is defined. So that's defined on a per process basis. So no other process has to bother about it. For the kernel stack, so what I was saying was we do it on a per process basis. But what you're asking is if it's maintained on a per process basis, then
Then how about the context?
how are we doing the context switch? So, so can we save the kernel stack for each of the different processes into some other location? Can we do that and then restore it? Can we do that? So that's my understanding as of now. But if I also get a clearer understanding, I'll share with you.
This context switching in the processes, it's like this system is taken by the OS.
Yeah.
But suppose our program is running, process is running,
Right.
and now it has some time is come for it to context switch to some other process B.
Right.
But it doesn't have the system call inside it, so that it can trap go into the kernel stack and from there it go to B.
Right.
Then how does OS take control and stop A and then switch to B?
So that's the exact thing. That's the exact question which we'll be answering now. So his question is actually very pertinent one. So if you don't make any system call, how do you assume control back to the OS? Any idea how do you do that? Okay, not you, someone else.
Sometimes
Okay. Someone else. Any other ideas? So program doesn't make any system call. The program keeps, like if the program is in execution, is there any way we can give the control back to the OS? So one of the ways to give control back to the OS is via making system calls. Whenever you make a system call, the OS now kicks in. You shift to a kernel mode, and now the OS can decide, do I want to execute process A, B, or C? But if that is not happening, if I as a program writer do not write any system call. So this happens very regularly, right? When we write programs, most of the time we don't write any system calls. But this does not stop the OS from running other programs. Right? So what do you think would be happening? While compiling, so this is one idea he's suggesting, while compiling you can introduce system calls, but that doesn't happen. So what Vidul was saying is the actual answer, that there are some, and Apoor was also pointing to it. So there are timer interrupts. We'll get to that in a minute. So switching between processes, is the OS running when the CPU, running on the CPU when the program is running? No. That's the exact question we've been discussing thus far. So how does the OS get back into control? So one of the ways is, as like some of you were suggesting, that's a very cooperative process. And this was something which was done in the initial systems. So each of the program was written by good people. So they would on purpose create some system calls, or they have the code written in such a way that system call would be invoked on a regular basis so that the OS can get back to control. The OS has to trust the processes to give back the control. Long running processes would periodically give up the CPU, but if I have to game the system, I would never make a system call. If I've got the access to the CPU, why should I give it to someone else? But what if so we don't make a system call. So some of them, one of the ways was to make explicit system calls if there is no system call requirement in your program. But that again, we said that we can game the system. So the other way to look at it is it's a non-cooperative fashion. So in the non-cooperative way of scheduling these processes, we don't want any of these, or we don't require any of these to explicitly make a function to make a system call. And so the other thing is that you might have the cooperative way of switching between processes, but there could be a bug in someone's system. So the only way to then get back to the normal running routine is to restart the system. But then we have a notion of a timer interrupt. So timer interrupt means that every few milliseconds or every few time units, an interrupt is raised, the OS gets back into the control line. So why would anyone from that side wants to take a shot at why timer interrupts are going to help you to switch between processes? So whenever a timer interrupt would happen, what program would be in control? The OS gets into the control. So the OS would now then execute at that point in time. And whenever the OS executes, then it always has an opportunity to context switch between different processes. So it's raised every X milliseconds. And okay, what do you think would be executed when the interrupt occurs? So what is executed when I press a key? If I press a key on my keyboard, so there is some code which executes to decode what the key is, and that code resides. So that code resides in the interrupt routine. So trap and interrupt are similar in concept, slightly different. So trap is for system calls and exceptions like 1 by 0, divided by 0, whereas interrupts are these asynchronous events. In this case, it's synchronous, like it's periodic. But interrupts would happen, when I press a key or whenever there is some data on the network. So what to execute when the interrupt occurs? The OS, similar to setting up a trap table, it sets up interrupt service table also. So corresponding to each type of interrupt, there is an timer interrupt. There is then these key press events or these hardware or network kind of interrupts. The OS correspondingly sets up a routine for each of them. Now at boot time, the OS also has to start the timer. So now do you understand that the OS is actually doing a lot of stuff. At boot time, it's doing a lot of stuff. It's like initializing the trap tables, it's initializing the timer, and also at the runtime, it's doing a lot of things. So let's revisit the previous execution. The only difference being that we'll now use the interrupt timers, and we'll set them up at the boot time. So initialize the trap table is exactly the same as before, but when you're setting up the trap table or the interrupt table, you're also now setting up a corresponding address to timer mapping. So for each time an interrupt occurs, a particular code will execute, and that code has a particular address. So that needs to be remembered. The interrupt timer is started, and it interrupts the CPU every X milliseconds. So this code is not exactly as the previous one. So let's say that we're not looking at all the things that we did previously, but we're only trying to understand what happens if an interrupt occurs. The process A is executing. 50 milliseconds or the timer interrupt has elapsed. So the timer interrupt is raised. Then what happens? You need to save the state of the current process. You save the states to kernel stack. You move to the kernel mode, and you jump to the corresponding trap handle. At that point of time, you can then switch between different processes. So you can. So if you look at this, corresponding to each process, there is something saved. So save register state to process structure it. So this is giving you some idea of the kind of data structures which are maintained, and you store all of these. Now, if you want to execute T, you have to switch from the kernel stack A to kernel stack B, and then you restore these registers, move to the user mode, jump to the program counter, and then execute. Does this answer your question, or do you? So it's a structure for maintaining the different parameters corresponding to a different process. Okay, so what happens if there are simultaneous interrupts? Or if a system call, if a timer interrupt occurs and simultaneously there is a system call, or if a system call is executing on my system and then a timer interrupt occurs, what happens then? Yeah.
When we are disturbing the distance from the drop source, so shouldn't the like why do we need this?
Why do we need the?
So why do we need this registers?
So if all the registers corresponding to B are not stored in the kernel stack, then you need this. So that's, again, I'm thinking out aloud. But the question really is, why is not everything stored in the kernel stack of B?
When we have a interrupt, it is not definite that we want to switch.
Right, right.
So, like basic things like PC and something like that are stored in the kernel stack of A. If we have
Sorry, what's stored in the kernel stack?
the PC and the
PC
like,
and the
basic whatever
Right.
they might be.
right.
So, and if the OS requires the context to switch,
Mhm.
so it calls context switch and then stores all the like all the remaining registers. Like it is basically for performance.
Okay.
I don't know for sure, but it seems like.
So do we all know that there are various registers stored with each process? Like various registers for each processor or submitted. A program counter, stack pointer, these are the basic ones. There are others which are being used, like the accumulator one. Accumulator. So what he's suggesting, and it seems logical that there are some other registers also which are stored just performance based. So you could like get everything back from the disk. But what he's saying is, why don't you save these registers at a faster access location? Okay, so what happens if we have simultaneous interrupts? Like a system call is being made, but at the same time you get a timer interrupt. Would either maintain a priority or, but can two of these execute at the same time? Okay, so which of these do you think will have a higher priority? A system call versus a timer interrupt? Why do you think that?
Because the need for the timer is so that this OS can get back the control. But any the system is going to do that as well. So program requires this system.
That's one logical argument. I don't know the answer. I was just wanted to have a discussion.
But
So the counter argument is that I can game the system by repeatedly invoking system calls, but if you make a system call, the OS gets back into action, and then it's up to the OS whether it wants to execute your process or some other process. So in that way, you cannot game the system.
But even if we are giving it priority, we can after the system will execute, we can do the timer.
Right, but so one shortcoming of this you can have so many interrupts coming together that if you don't handle them properly, they'll get lost eventually. So either you keep on storing them and then buffer them up, or the easiest way to handle this is to whenever an interrupt occurs, you disable all the other interrupts, so that interrupt doesn't happen. So you don't need to have to prioritize between them. But there are more advanced methods of handling this, which you'll probably see in the next few classes. Okay, so we'll now start. So now we finished the CPU virtualization side of things. We'll now start the memory virtualization side of things. So, any doubts in the whole of CPU virtualization till now? In the big picture. Let's forget the small picture, this particular lecture. But if you look at the big picture, any doubt in the CPU virtualization?
So I had a doubt in the track table. So in the track table, suppose the first column will be the system call number, and the next will be the address column.
Right.
So how does the OS know that this is, or the program know that this system call is mapped to this system call number?
this system call is mapped to this. So that's set up. So that's exactly the. So it's a common so system call handlers. Each of them have a separate number associated with them. Let's say open has number 0 associated with them.
So it is predefined.
It's predefined. So POSIX will have one particular set of numbers. Maybe Windows has some other set of dimensions. Okay, so we'll start with memory virtualization now. So in the early days of multi-programming, in the early days of when OS were being used, the memory of or the address space would look something like the entire physical memory. You have the operating system. So as we've seen that each of the programs have code, data, heap, and stack. So the operating system is also programmed. So it also has code, data, stuff. And the other is left for the other processes. The other memory, physical memory, is left for the other processes. So I'm sure. So just to be sure, does everyone know what I mean by physical memory? Okay. Do I mean the hard disk SSD or do I mean the RAM? RAM. So everyone is clear on this, right? So in the early days, what you do is to make things simple, you just run a single program at a time. So in the sense that you have a single program would have access to the entire physical memory space. So why would you do this? Like what problem is this avoiding? If you just have a single program running on, like occupying the entire RAM.
Like the context which you need to store.
No. So what are you saying is the opposite thing? So what is sorry?
Illegal access.
Illegal access. So it's fairly easy if I only have a single program in the entire RAM. I don't have to worry about program B illegally trying to access my data. So we just have a single program. But what's the shortcoming? Whenever you have to run multiple processes or you have to do context switch, you will move all of this RAM corresponding to process to the disk. And how quick is the RAM compared to the disk? Do we know any numbers? Sorry? So you write to the disk, and correspondingly, if you have to bring the other program into the memory, so you'll have to again read it from the disk. Very slow process. So you should look up these benchmarks of HDD versus RAM versus SSD to give you a fair idea of why this is a bad idea to have a single process in memory at a given point of time. So what we now usually have is a concept of a shared memory, where we have multiple of these processes, each of them having their own code, data, heap, and stack, and all of them lying in this RAM, in the memory space. Now, one thing you might be already wondering is, so the operating system has to somehow maintain this list of all the free spaces. It also has to maintain the starting address and the ending address of each of the process address space. So this is again an additional thing that the OS has to do. So what's the risk with having multiple of these programs? It's as I use 26, 27. As I use 27 was saying, that the risk is that programs can access others' memory. So that's why this is a slightly more complicated problem, but we need to handle it given that it's a fairly common thing that we want to do. So we look at the address space again. We look at it in more detail. So we have the program code, heap, and the stack. So let's keep it to only these three at this point in time. So what it's done is actually heap and stack are at the other end of the address space. So they grow in different directions. So this is one implementation. In some other implementations, you might see stack right after the program code and the heap is towards the end, and they again grow in opposite directions. Now, are you wondering why program code doesn't grow? Why does the program code grow? So stack can grow in size, heap can grow in size. Why doesn't the program code grow in size? Because it's a single code. So why would the program code? So it's the set of, let's say if I've written a C program, it's converted to an assembly. It won't change at runtime. The heap and the stack are the only thing which can change. So what we generally see when we run malloc, or if we're looking at the different addresses in a C program, what we get is virtual address. So these programs generally don't, until unless we're doing something crazy, we don't see the physical addresses. We see only the virtual addresses. Why are these virtual? So why are these addresses called virtual addresses? So every program will think that its address space is from 0 to something. It may or may not be 0 to 16 KB, it may depend on the implementation or different implementation. But so this is not the actual physical address. So this is the question which we need to in fact figure out. So where is my program located on the actual memory? Why do we want to do that? So why do we need physical addresses? Why is virtual address not enough by itself?
The actual address that is present in process A, it will be same as another address,
Right.
virtual address in process B. But we cannot have the both of them are actually the same location in the actual physical.
Right. So the reason why we need physical addresses is because this is while virtually it seems that it's located at 0 KB, but physically it may be located at 40 KB in the memory space. So if we want to execute something, we want to go to the exact location of where something is being stored. That's why we require the physical address space. So there are few goals of an operating system to make memory virtualization more efficient and more competent. The first is transparency. We want the virtual memory to be invisible to the user program, in the sense that each program will think that they have the entire memory to themselves. So when we write a program, we generally never worry, right? Whether I get some free space or not, or whether the free space, we go back to this, or whether this memory or this RAM is fragmented or not. So by fragmented, I mean that there are a lot of free spaces in between. Or why are these all not contiguous? We don't need to bother about any of these things because the OS is doing this on our behalf. The other is efficiency. So we want to ensure that all the processes are running very efficiently. They don't slow down because of the OS overheads. And it's not just the timing efficiency, but also the space efficiency. So we don't want to store all of the contents of all of the processes into some other structure. That will take a lot of space. But one of the more important ones, which was the one which we started by motivating the need for if we have multiple of these programs running in the same address, in the same physical memory, we want to protect processes from each other. So I think we should end at this point and discuss more of the memory virtualization mechanism in the next class.